One thing you're starting to see more of in the aerospace industry is flexible aircraft. Most of the time, flexible behavior is seen in aircraft that are designed specifically for surveillance and reconnaissance purposes. And the main reason for this is that often these are the types of planes that need to be able to travel at very high altitudes for very long periods of time. In order to have this kind of flight performance, a lightweight design with very slender, high aspect ratio wings is needed, which often results in the design being very flexible. One of the problems with designing these high-altitude, long-endurance aircraft is that a lot of the nonlinear aeroelastic design software out there is still theoretical at this point and hasn't been validated against experimental data. So the purpose of Xhale, which is the research project that I was involved with this summer, is to create a remote control aircraft that can be fitted with different kinds of instruments in order to collect data that can then be used to validate existing code. Working on Xhale this summer, I did a lot of hands-on design work creating parts for the existing aircraft, and one of the parts I spent a lot of time on was a camera mount stiffener. What's unique about Xhale is that it actually doesn't use strain gauges to measure the deflection of the wing. Instead, LED lights are embedded along the wing, and cameras mounted on the center of the aircraft are used to capture the position of the LEDs, which can then be used to calculate wing deflection. A problem we were having with this is that the mount used to secure the camera onto the aircraft wasn't rigid enough, and the cameras were starting to vibrate back and forth, which threw off their measurement. So these are the left and right camera mount stiffeners, which were designed to make the camera mount more rigid and reduce vibration. They're mirror images of each other, and the aircraft right here is actually upside down right now, but normally they fit over the wing like a sleeve on either side of the center spine like this, and each one has 3 attachment points. The front and rear attachment points connect to the front and rear cameras, and the center tab right here connects to the underside of the wing, which is actually the top surface right now since the aircraft is upside down. Prior to this summer and before I was involved with the project, there was a lot of flight testing that was going on. There are actually 2 vehicles currently built for the Xhale project. One is called the ATV, or Aeroelastic Test Vehicle, which is fitted with all of the expensive sensors. The other is the RRV, or Risk Reduction Vehicle, which doesn't have many sensors and is used mainly to make sure that the aircraft is flyable before the more expensive ATV is used. The model being tested before was the RRV, which had several successful flights that all took place without fairings attached to any of the spines. When additional flight tests were carried out with the RRV, this time with the fairings on, it was found that with the addition of the fairings, the aircraft had a strong tendency to pull left, so much so that the pilot couldn't correct it. And because of this unexplained behavior with the addition of the fairings, we began conducting a series of wind tunnel tests this summer of the spine, both with the fairings on and fairings off, to see if we could figure out what was actually going on. Before we could use the data we collected from the wind tunnel tests, there was a fair amount of work we had to do first. We actually had to manually enter all the data into Excel because the way the wind tunnel software reported it, there was no convenient way of doing this. Amongst other things, we also had to rotate the coordinate system that the data was reported in because the coordinate system the wind tunnel software used was aligned with the sting that the model was mounted on, which is not what we wanted. Once all of the data was entered and modified, we finally were able to start making different graphs to try to understand what was going on. Most of the graphs I ended up creating were plots of the forces and moments acting on the model at different angles of attack as a function of the free stream velocity. Unfortunately, we didn't finish analyzing all the data from the wind tunnel test before the Xhale program was over, so I haven't actually gotten to see the end result. But other than that, getting to do research through the Xhale program was a lot of fun, and I learned a lot too, and I'm really glad I got the opportunity to participate.